Good afternoon and welcome to day 2 of our 7th annual 3D metal printing experience. Presented online as a 2-part webinar series and hosted by 3D Metal Printing Magazine. My name is Lou Krenz, Senior Editor of 3D Metal Printing, and I'm pleased to serve as your moderator today. Thank you all for attending, and thank you to our sponsor, Solar Atmospheres, for helping to make this informative event possible. Before we get started, just a few business notes. The entire event and each presentation are being recorded for archiving and will be posted to the 3D Metal Printing website within the next couple of days. We'll let you know via email when the recorded event is available for viewing online. And all attendees are in listen-only mode. Speakers and other listeners will not be able to hear any audio from your site during the program. However, you do have the ability to communicate with us throughout the event by submitting your questions and comments using the question box located on the right-hand panel on your GoToMeeting screen. Simply type your question to an organizer and as selected from the drop-down menu. You'll also use that same question box to ask questions of our speakers at the end of each presentation. Finally, we'll make the presentations available to you saved as PDFs in the next few days. Look for an email from us to let us know how to access them. Now it's time to begin today's webinar session of the 3D Metal Printing Experience. Today we will hear from 3 speakers with short breaks included in the schedule. Our first speaker, Mark Norfolk, is president of Fabrasonic LLC. Mark has more than 25 years of experience in manufacturing, research and development, as well as shop floor management. He currently leads Fabrasonic in the commercialization of ultrasonic additive manufacturing, having previously led EWI's development and research into the ultrasonic process for AM prior to the inception of Fabrasonic. Before joining EWI, Mark worked in various roles at Deere & Company. Mark's presentation today is titled Solid State 3D Printing for the Aerospace Industry. Please welcome Mark Norfolk.
All right, thank you, Lou. I appreciate the introduction. Good afternoon, everyone. I hope everyone's doing well today. I know we'd rather have these events in person, but you can. I'll see if I can turn on my camera here so you can be frightened away by what I look like. So, again, my name's Mark Norfolk, a welding engineer by training. As Lou mentioned, I spent about a decade at John Deere making tractors and then somehow fell into this 3D printing thing. So today I'm going to tell you a little bit about a process that's not widely known. It's beginning to get a little larger, but ultrasonic additive manufacturing. It's a little bit different way of doing metal 3D printing. Just kind of as a gauge. Last year, UAM was used to make about 8 million parts. This year, we're shooting for about 20 million parts. So it is being used in production. It's just not most of the applications that it's being used for we can't talk about, which is unfortunate, but the way business is. All right, let me see if I can. There we go. So first, I'm going to tell you a little bit about what ultrasonic additive manufacturing can do. Then we'll look a little bit on how we actually do that. And lastly, I'm going to walk you through some use cases, some specific examples of how UAM is being used specifically in aerospace. So the first thing that UAM does well is produce complex internal geometries. And you might be sitting there thinking to yourself, well, yeah, all 3D printing processes are good at making complex internal geometries, and that's true. What makes us a little bit different is all of our machines are hybrid. And when I mean hybrid, I'm saying additive plus CNC milling in the same package. So all of our internal passageways, internal channels, internal voids are going to be CNC milled. In fact, all of our systems start off life as a CNC mill, and we print near net shape, but every surface is going to be touched by a mill. So you can get highly accurate internal cavities as well as very smooth, CNC quality surface finish on the inside of 3D printed parts. There we go. The second thing that we do well is embedding electronics. Ultrasonic additive is different from many traditional 3D printing processes in that we don't take a metal like a powder or a wire and melt that. We're actually taking thin metal foils. The foils are on the range of about 5/1000ths of an inch, and we weld those together at room temperature using a process called ultrasonic welding. Ultrasonic welding is not a new idea. It's been around since the 1960s. Early on, it was called wire bonding in the electronics industry. What we've done is taken that 1960s technology that used maybe 50 watts of power to weld small wires in electronics, and we've scaled that up to about 10,000 watts so that we can weld thin films layer by layer to produce three-dimensional shapes. The beauty of using ultrasound is it's a solid state process. That means there's absolutely no melting. In fact, most of the parts that you're going to see throughout the presentation today never got above, say, 200F. So the lowest setting on your oven at home, that's as hot as these parts ever get, and only for a very short time. At any given point in a 3D build, we're only seeing that temperature for, say, 100 to 200 milliseconds as the welding device is rolling over the surface. Because of this low temperature, it allows us to embed pretty much anything in solid metal parts. Most of the time, that pretty much anything happens to be some sort of electronics package, and I'd say 75% of the time, that's some sort of sensor. What we do is we print metal to a certain height. We come in with that CNC mill. Again, all of our systems are hybrid. We mill away a little channel, a little groove. We drop in that electronics package, and then we continue welding right over top of it. Because it's so low temperature, because it's such a soft process, we don't damage those complex electronics packages. So in the center picture here, you can actually see a fiber optic cable that's been embedded in a metal part. And if you can embed a solid glass fiber, you can pretty much embed anything. The nice thing about fiber optics is you can turn a fiber optic cable into about any sensor you want. Acceleration, strain, microphone, temperature, pretty much anything can be done with a fiber optic cable. We really like them because they're small and easily integrated into complex structures. On the left-hand side, you have some traditional thermocouples that have been embedded in plates, and this is something we do almost every day. It's pretty common. On the right, we have a USB stick just to show that it doesn't have to be a sensor. We can do other electronics, controls, tracking devices, Internet of Things. All of those are available when you're printing with the solid state process. The next thing that we do well, again, is derived from the fact that we're not melting and derived from the fact that this is a solid state process with no melting. And that's make dissimilar metal structures. So really the sky's the limit here. Layer 1 can be aluminum, layer 2 can be copper, layer 3 can be tungsten, layer 4 can be tantalum. Just layer by layer, we can swap materials. Now, if you were going to take the bottom right there, aluminum and copper, and you melt that using a traditional melt-based approach, when that resolidifies, you're going to get an intermetallic. And the problem with intermetallics is they tend to be very brittle, almost like a glass. So they're not a material that is typically desired in engineering. Because we're not getting hot, because we're not creating any sort of melt pool, we can mix these dissimilar metals layer by layer without having to worry about the metallurgical consequences of mixing two dissimilar metals. Now, one note of caution, certainly if you take these dissimilar laminates and you throw them in salt water, there's corrosion potential there, so you have to still think through the engineering of your products. Similarly, if we take that aluminum and copper and we put that in service at 600C, we're going to start diffusing one into the other and start creating intermetallics. So we still have to use good engineering judgment, but it does give us the ability to kind of put any metal anywhere in the structure that we want. Some applications of that, the aluminum copper is used all the time for thermal. We mix that combination to kind of get the lightest weight, highest thermal conductivity structures possible. On the top left, we have layers of tantalum, aluminum, and I believe tungsten. That's actually used for radiation shielding. for satellites in high radiation environments. That's something we do a lot of. Customers provide us with a template of a radiation shield that has different metals with different atomic numbers, Z numbers, and this allows you to create a very effective shield at a very low weight. On the bottom left, we have tantalum on the stainless. This is actually more of a cladding application. But again, because of the low temperature nature, we can clad a thin layer of highly corrosion resistant tantalum onto a less expensive base of stainless steel. Other applications are gradients. We make armor products that are gradient. We make gradients that go from one CTE to another. The sky's the limit in kind of engineering new materials by layering dissimilar metal layers. Along similar lines, we do a lot of work with metal matrix composites, and this is mostly in the aerospace field. On the right-hand side, you can see some black dots on the edge of our material here. Those black dots are actually continuous ceramic fibers. So we're printing continuous ceramic fibers into an aluminum matrix to make a high stiffness metal matrix composite. If you can name a fiber, we've probably embedded it for someone. Carbon fibers, basalt fibers, S-glass, you name it, it's probably been embedded. But the idea is to make a metal matrix composite. And just like any polymer-based composite, we can play games, 0, 30, -30 to build strong laminate structures. So those are some of the highlights of what the process really excels at. Now I'll show you a little video of the process in action. As I mentioned, all of our systems start off as a CNC mill. Here we're milling away some material. And in our process, a majority of the time, we're starting with some pre-existing feedstock. We don't necessarily have to print the entire part. Customers bring us casting, customers bring us weldments, and we start printing from the feature that requires 3D printing. So we may only print 30 or 40% of the part, but that saves us time as 3D printing is kind of slow and expensive. Printing just the portions that need 3D printing really helps speed things up. Now, underneath that yellow box, you see a little cylinder rolling. That cylinder is actually the welding device, and I'll explain that in more detail later. But as that roller is rolling over a thin film of foil, again on the range of 5 to 10 thousandths of an inch thick, it's welding down that metal foil, fully dense, 100% metallurgically bonded metal. We repeat this welding over and over again. Again, we print near net shape, so we're printing kind of boxy structures that are close to the shape we want. And we derive all of our geometry specifically from the CNC milling. So from time to time, we'll stop, switch over to the mill to create the geometry as we build up layer by layer. Again, all of the UAM systems are based off of a CNC mill. So we can choose different size mills depending on the product that we're trying to build. Our largest system right now in-house is about 6 foot by 6 foot build envelope by about 3 foot. So we can make some fairly large parts. We've had some customers that have put our welding devices on other motion systems like robots, fiber placement machines. So the scale of the process can be quite large. From a deposition rate, when you look at some of the powder-based processes, you hear numbers of say 1 to 4 cubic inches an hour of volume. We're printing more on the order of 40 cubic inches an hour. So it's a little bit faster, but we would never call it fast. It is still a fairly slow process. Again, for many of our parts, we'll start with something that's already existing and add material to it. To kind of leverage that ability without having to spend the money to print the entire part. And again, most of our machines are CNC mills and typically 3-axis, although we've done a few customs that have a few more axes to them. So a little bit on how the process actually functions. Again, the idea of using ultrasound to weld metals is not new, again, derived in the 1960s from some electronics, wire bonding they called it. What we have is an ultrasonic horn, that's on the left-hand side here. And what that is an acoustically tuned device that's meant to vibrate specifically at, in this case, 20 kilohertz. On either side of that, we have a transducer that turns electrical signals into mechanical motion. So they're basically piezo ceramics. We put a voltage on them, they get bigger. Take a voltage off, they get smaller. You do that 20,000 times a second, and you can get this entire stack to vibrate left to right on the order of, say, 20 to 30 microns. That vibration is what's actually creating the solid state bond. As we're vibrating left to right in this page, we're rolling out of the page toward you, and we're rolling over some sort of metallic feedstock. The great thing about foils as a feedstock is you can buy them to an ASTM spec. Industry in general has been making metal foils for 70, 80 years. It's a very mature space. And that means those foils are fairly inexpensive. For 6061, an alloy we use a lot, right now for foils, we're paying on the order of about $6 a pound. So the foil feedstock not only gives you, a relatively inexpensive feedstock, but also one that can be bought to a spec. Because we're not creating any heat during the welding process, we don't really change the base material properties of the incoming feedstock. We're not changing grain size, we're not changing precipitate size. We're really getting, what's coming in is going out. On the right-hand side, we have depicted a CNC mill. Again, from time to time, we can come in with the mill and create both that internal and the external geometry. Pretty much every surface in an ultrasonic part is going to be touched by a mill. A little more detail on the bonding mechanism. Get a lot of questions about this. It's akin to other solid state welding processes such as friction welding, explosion welding. But the general idea is metals like to stick to other metals. But down here on Earth, all of our metals are covered with an oxide layer. So if we take two pieces of metal and we slam them together, what we're really doing is slamming together two thin layers of oxide. The idea with an ultrasonic bond is to remove that oxide. So what we're doing is we're taking that welding horn, vibrating it left to right, and that's scrubbing the microscopic ridges and valleys on those metals. It turns out that most metal oxides are very, very brittle. So that scrubbing motion basically grinds away the oxide layer, kicks it out the side, and we have virgin metal on virgin metal. We apply a little bit of pressure, a little bit of force, pushing those asperities together, and we get a solid state bond. Now, certainly there's more to it than that, but that's the general idea. Is we're scrubbing to get rid of both the oxides and any contaminants. That exposes virgin metal on virgin metal, allowing us to get a solid state bond. To build up a three-dimensional shape, we take these thin metal foils or these thin metal strips, and we lay them up kind of like in a bricklaying pattern. Certainly, we don't have to do that. It's kind of a belt and suspenders approach to make sure that if we miss laying a tape in the wrong place, that our bond lines aren't all in a vertical seam. But we take those, laying up in a bricklaying pattern to build up a solid three-dimensional shape. Again, all of the geometry is going to be derived finally from CNC milling. So we're printing close to the shape that we want, and then milling to the final shape. In addition to kind of strip material, for some applications, kind of higher volume applications, we can use kind of pre-cut sheets, the sheets that are cut to the approximate dimension of the part. That allows a kind of faster motion of the machine, but you typically don't do that until you get into a little bit of a higher volume part. So just from a quick metallurgy standpoint, this is a metallographic cross-section of copper printed onto aluminum. I think the thing to note here is without those red lines showing you where the interfaces are, you really wouldn't know where the interfaces occurred. It truly is a solid state welding process. We're getting 100% metallurgically bonded material. It's solid, it's dense, and we can mix materials all in the same buildup. That gives you a general idea. Certainly, as we make larger and larger parts, there's better ways to inspect, but just looking at it from a cross section, this gives you a good idea of the quality of the process. Now, I mentioned earlier the ability of UAM to weld dissimilar metals. This chart right here was actually derived for that 1960s technique of ultrasonic wire bonding. We have not tried every combination in this array, but we've certainly tried a lot. We've put aluminum onto about everything. Tantalum onto steel, tantalum onto aluminum, tantalum onto copper. We've recently been doing a lot of work with zirconium. We've done tungsten to steel, tantalum to steel, tantalum to, or zirconium to steel, pretty much every kind of nickel alloys to steel. You get the picture. There's a wide array of different dissimilar metal combinations that we can make in order to create a custom material. The few items that really don't work well in an ultrasonic weld are things that are self-lubricating. So let's say you have a cast aluminum, let's say that's maybe 5 or 6% silicon by volume or by weight. That silicon acts as a lubricant and makes it difficult to weld. Similarly, things like lead that are self-lubricating don't do well with the process. The image at the bottom left, I want to kind of make a little distinction here. We're seeing some silicon carbide fibers. Again, we've embedded pretty much every type of fiber you can imagine. Embedded between aluminum and copper. And in this image, I would say the aluminum is metallurgically bonded to the underlying copper. But I would say that silicon carbide is embedded in the aluminum. So the welding process works very well to weld metals to metals, but it does not weld metals to non-metals. So anytime we're working with some sort of non-metallic, we're going to embed that. And when I mean embed it, these fibers were actually just laid on top of the copper and we welded an aluminum layer on top. And you can see we've extruded metal all around those fibers. Under a high power ultrasonic field, metal flows very easily, so we can extrude metal around things that we're embedding. A few more images here just to show you some of the dissimilar metal combinations that are possible. Titanium to steel seems like an odd one. That was actually for ice skates. Nickel to stainless for corrosion, tantalum to steel for corrosion, aluminum to stainless as a transition joint. We've actually arc welded to the stainless steel on one side and arc welded to the aluminum on the other to create a dissimilar metal transition. A lot of these applications right here I would consider cladding. Certainly we're building them up layer by layer, so it meets the definition of 3D printing, but the end goal is to clad material A onto cheap material B typically. Looking at more along the lines of custom materials, we see some gradients here. The titanium aluminum gradient is heavier in aluminum on the top and heavier in titanium on the bottom. And this was actually designed as an armor product. So we're engineering a material with a variation in the material properties through thickness. Below that on the left, we have aluminum and copper and stainless steel. A lot of the thermal problems that we get involved with involve copper to wick heat away, but a lot of those devices tend to be stainless steel. So the ability to mix stainless and aluminum kind of at will in a design to wick heat away is important. In the center two images, we have aluminum combined with Invar and aluminum combined with moly. You can think of a gradient of CTEs. We can't show many of those because they're proprietary, but the idea is typically to go from the CTE of silicon to the CTE of a heat exchanger, whether that be aluminum or copper. And so you intersperse layers of, say, Invar or moly that have a close CTE to silicon, and then you gradually change to more and more by volume of that aluminum or copper. So there's a wide array of materials that can be engineered by 3D printing to get the exact properties exactly where you need them. We've done, variations in modulus, variations in CTE, variations in thermal conductivity, all within the same part. This is another example of metal matrix composites. In an earlier example, I showed some fibers that were on the order of about 80 thousandths of an inch. These fibers here are more on the micron range, 5 to 10 micron fibers. Again, the little white dots at the bottom, those are actually continuous alumina fibers, so Nextel fibers. And we've embedded those in aluminum matrix. And you can see we have varying planes of this material, and those are oriented in different directions. And just like any other composites, metal matrix composites, built this way follow the rule of mixtures. So we can easily calculate performance based on kind of traditional composite theory. The only thing is our matrix of aluminum is 45 KSI and our fibers are maybe 200, 250 KSI. So you can make some fairly high performance materials. So we talked about embedding of sensors into solid parts. And again, I'd say this is a large application space for the UAM technique. Typically, we're trying to do either health monitoring, or if we aren't doing health monitoring, we're probably trying to calibrate someone's model. By being able to get data in a very specific location and feed that back, we can calibrate people's models. All the models kind of have an analytical equation with three unknowns at the end. Embedding sensors exactly where you want to get that data is really helpful for calibrating those models, or again, for monitoring the stress rate in a part while it's actually in operation. So here we have some work we did for NASA Langley. We embedded some fiber optic strain gauges into an aluminum plate that they have a lot of history of the design and analysis of this plate. And it was interesting, we were able to actually collect data while it was being cyclically loaded. We were able to see cracks appear and actually watch the plastic zone of the crack as it approached the fiber optic sensor. Of course, at some point, the fiber optic sensor broke, but it was interesting that we could actually watch that plastic front move closer and closer as the crack evolved in the part. On the bottom right, we're showing that ability again of ultrasound to flow metal around a solid metal part. So again, these are fibers on the order of about 150 microns, and we've flowed aluminum all the way around them. The fiber on the right is a glass fiber coated in aluminum. The one on the right is a glass fiber coated in a polymer. So that polymer moved around a little bit, but we were still able to extrude metal and get good interaction between the sensor and the matrix, which is important for getting good data. We find that we can typically, hold good high quality data till 2 or 3% pass yield of the underlying base material. So you can get data pass yield, but certainly there are limits. So a few more examples of heat exchangers. This typically is one of our primary applications. The ability to make complex antonal shapes that are CNC milled so they're smooth and accurate, as well as the ability to combine dissimilar materials allows us to make a lot of different thermal devices. So again, putting together aluminum plus copper, copper plus stainless, copper plus nickel, to create a high performance device and getting those channels and those flow paths exactly where you need them. On the bottom right, we have a quarter there. Next to that quarter are some channels. Those channels are about 1/7 of an inch. So we can make very, very fine channels right where you need to pull heat out. But in larger structures, those channels can grow up to sizes of an inch or more. And throughout the device, we can change the scale. So the top right is what we call a harmonica. Those channels are about 150 thou wide by about 6 thou tall. So that's a very dense flow path. But in that particular part, about an inch away, that turned into a header that opened up into a larger flow channel. So throughout the part, we can change the contour of the inside shape of those flow paths, which gives the designers a wide berth, a large ability to make very, very intricate designs for thermal performance. So those are some kind of high level just examples. I'm not going to try and walk through some specific case studies that we've built parts for aerospace. Certainly we've made other parts that we can't share, but these are mostly going to be from government agencies like NASA, where we're allowed to share pictures and results. So the first example here is a set of heat exchangers. The black part is a radiator for a CubeSat, so a small satellite. The black part, again, is about probably 16 inches long and is meant to radiate heat away from the spacecraft. On the right of that, we have an aluminum printed part that is actually a mount for a cryocooler. The polymer part on the right just shows the geometry on the inside of that mounting plate for the cryocooler. And this entire system has been proven out and approved for space flights through Utah State University did the design and NASA JPL did the testing. and a version of this is going to fly later this year. But it gives you the idea of how you can highly engineer thermal systems for both kind of optimizing weight and thermal performance with a 3D printed part. Just to show you kind of an idea of how this type of part is made, this is a separate cold plate, but it's the same general idea. For the most part, we're starting off with a piece of billet. Again, only 3D print those features that need it. We print a little bit of material just to get our process established. Then we go in and mill the internal channels. Now, this doesn't have to be a single layer of milling, but in this particular example, we have one layer. Like all other 3D printing processes, we have a need for support. When we're welding, we're pushing down with a fairly high amount of force. So any channels wider than, say, about 1/4 of an inch, we're going to fill those channels with a water-soluble support material that's patent pending with Fabersonic. We then mill that to get a nice, flat, even surface. And then we continue to print metal foils layer by layer over top of those channels to fully encapsulate those. When we get done with all of our printing, we come in with the mill to get the exact geometry, in this case, an isogrid that we're looking for on the outside of the part. Just to give you kind of a range, these parts here were helium leak check tested down to 10⁻⁹ standard cc's a second of helium. So that's kind of space flight qualification numbers. Burst pressure tests on these parts were about 3,000 PSI, and operating, I think, was only about 200, 300 PSI. Again, on the bottom left, we have a combination of aluminum and copper. And again, that's a common theme. Mixing metals with complex shapes, with embedded electronics, all in the same part to get a very optimized design. Another part in a similar vein is a part we did for NASA JPL. This one was actually meant for the Mars rover. Unfortunately, the testing regime that the JPL needed to complete was delayed and was not finished in time to make flight. The good news is we did pass all of the tests. The bad news is we didn't get to fly. The bottom right picture kind of shows a comparison of the traditional way of making a heat exchanger for some of these interplanetary vehicles. What historically has been done is taken a piece of billet aluminum, milled some sort of ortho grid, and then they actually take a sawzall and cut out some of the ortho grid, and then they go in and epoxy a stainless steel tube onto the aluminum, and then they cap that with an aluminum saddle, again, epoxied in place. So you can imagine that the epoxy is not that great for thermal conductivity, and all of the bolts and all of the saddles add a considerable mass to the process. So what we were trying to show here is that 3D printing could really pull both mass and improve performance. So the part at the bottom left was printed using UAM. It was a one-piece integral part printed all at one time. We were able to save about 30% of mass without any design changes. We just took the standard design and built it without the saddles. And we were able to get a 30% weight production, turned it around in 3 weeks. Like all 3D printing, you can turn around things quick. And we were able to get about 30% better performance because it was monolithic aluminum as opposed to a mixture of dissimilar metals and epoxy. Another kind of slide of pictures of that. Again, that part went through quite a bit of testing at NASA JPL. The bottom two images here are some CT scans. And all the CT scans came back clean. Again, pressure tested, helium leak tested, vibration tested, thermally shock tested, and passed all of JPL's requirements. Along the same lines, this is another heat exchanger, similar pedigree. And here we're trying to show that the internal passageways can be machined specifically to get different flow rates, different cross-sectional areas. The cross-section on the left, we just made a custom CNC mill. We had that milled for about $45, $50, and then we milled the internals of those channels just like any other channel, but we're able to get a lot more surface area, get thin structures. And then just like any of our other heat exchangers, we print a lid over top of that to seal that in. So from a design perspective, there's always things that can be done to change cross-sectional areas, insert fins, insert turbulators, all those type of activities that people might be doing with other processes can be done just via CNC milling as opposed to some sort of powder-based printing. Another area we do a lot of work in is larger heat exchangers. Here we have pictures of a heat exchanger that's about 5 foot in length. We've done some larger ones that we can't show. And I would say, one area of real interest for us right now is combining additive processes. So a powder bed system may be great for making organic bone-looking structures that are really good right at a place where you're trying to pull heat out for getting really high surface areas in something like a vapor chamber. We've combined powder bed processes to create those very fine structures that really aren't a sweet spot for ultrasonic additive. We've printed those on powder bed and then used additive UAM to embed those in much larger heat exchangers. So I guess the idea I'd leave with you is we don't have to print all of one part with one process. We're doing work where we're combining UAM with DED processes, with powder bed processes, as well as cold spray processes. And it's really about using the right tool for the right feature. I think 10 years from now, just like we have a mill, a drill press, a lathe, you're going to have an ARC DED with a powder bed with a UAM system, and you're going to use those processes that are best for a particular feature, combine those to make a complex 3D printed part. But I'll get off my soapbox. Another kind of case study is looking at some of the metal matrix composites. And the idea here is really just to show you how a little change in mass can have a huge effect on performance. This was another program for NASA Langley on a similar geometry that we looked at in the embedded sensors. We printed one completely monolithic out of 6061. So the whole thing was printed 6061. And then we printed another one with 6061 and about 10% by weight metal matrix composite, so Nextel fibers in this case. And then we put both of these through a testing regime. The monolithic printed 6061, we started seeing cracks at 100,000 cycles, and we had 2 parts by about 200,000 cycles. But by adding just a little bit of ceramic fiber, the crack initiation pushed out to about 500,000 cycles, and we actually ran out of test money at 20 million cycles. So again, by combining materials, combining dissimilar materials in a very specific way, you can get huge gains in performance. And we do a lot of work, with metal matrix composites, with very elegant designs, by using UAM to combine the similar materials to get a much more effective, more optimized structure. Along the same lines, I think we looked at this earlier. These are some larger fibers. These fibers are more on the range of about 80 thousandths of an inch. It's the same idea. Let's add, rebar and concrete. In this case, we have ceramic fibers and aluminum. We looked at this part already, but I wanted to mention it again just to give the idea of digital twin. There's a lot of activity at aerospace customers, aerospace OEMs, trying to understand and model physical parts and have an analytical copy of that part for testing and rapid evaluation. UAM is used in that space all the time. As I mentioned, you can embed sensors and then use those sensors to correlate a model. You can embed sensors in the actual physical part and watch, the evolution of loading in that part over time, and then, watch that in your model at the same time. So there's a lot of work that we've done, especially recently, embedding sensors in these parts so that we can get data throughout the life of the part while we're correlating that with some sort of analytical model over time. One example of that is what we call the sense pipe. This was some work for NASA. They were interested in looking at both pressure and temperature fluctuations in a cryogenic fuel pipe while fuel is flowing at the rocket. So here we embedded some fiber optic sensors so that we could measure both strain and temperature along the length of the pipe and get some fairly high resolution data as the rocket is consuming fuel, we're measuring the kind of changes in pressure and temperature as that cryogenic fuel is kind of flowing through the pipe leading up to the rocket. This same idea has been used. We've built similar type pipes for oil and gas, for nuclear reactors. Again, the idea is you can embed sensors in the ID of a pipe, OD of the pipe, and get data forever and a day from those sensors that are buried in a nice safe place inside the metal of the part. Another similar example, this was another job with NASA Langley. They were looking at a drone and trying to correlate flight data with actual computer models. So here again, we embedded fiber optic strain gauges into a bracket for a drone. And we were able to collect true strain time histories as that part was loaded in the field. And that data was fed back into the development of a model or the model program so that we could get actual true strain time histories as the part was being used. And this isn't just used in aerospace. We're embedding sensors in actually machining equipment so that we can get data from machining equipment while it's in operation, automotive, off-road vehicles, all the applications where you want to get data as that component is in the field and get that data over a long period of time. Embedding sensors is a great way of allowing engineers to get that sort of information. All right, I think we're down to 2 more case studies here, and then we'll open up for questions. This example right here was for a rocket company called TGV Rockets. In the rocket world, most rockets are kind of binary on or off. There's not a lot of ability to throttle the flow of those rockets. This is actually a fuel injector that we made for TGV that we embedded a servo motor in the center of the part. So you can see right here, we have a motor, we have some gears, we have some bearings. And that servo motor was actually controlling the position of a pintle and allowed TGV to kind of increase or decrease flow of both the oxidizer on the outer portion and the fuel on the center portion as that rocket was being fired. So this is just another example of how embedding electronics, embedding controls in a solid metal part can give you the capability to make a part that you traditionally wouldn't be able to make. Because we have those cryogenic fuels flowing around this, getting that mechanical device on the inside is not a trivial pursuit with traditional manufacturing. But with additive, we can drop in that electronic, route a little wire out to the outside so that we can control it. And that motor is forever protected as it's buried in solid metal. Another example here, you can see on the bottom right, a layer of copper. We printed dissimilar materials, the aluminum mostly for mass, but that copper was actually a seal. It was a knife seal for the pintle on the top. And that's just another example of how you can use multiple capabilities of a 3D printing process to get value out of your part. We've done some parts in aerospace. I can't share those examples, but where we've printed metal matrix composites to get a high performance structure. We've embedded channels in that same structure to take care of thermal. We've printed, tantalum tungsten for radiation shielding in that same structure, as well as embedded electronics, all in one structure. So taking all of those capabilities and designing around the capabilities that now exist allow you to make a very tight, optimized structure, which is certainly beneficial in the aerospace world. So the last topic to talk about is printing in space. And this is an area we're just starting off our 3rd program with NASA on printing in space. The first program really looked at how can we shrink down our welding process, both from a mass standpoint as well as a power standpoint. The idea or the reason while UAM might be a good application for printing or welding in space is, again, it's a solid state process. We don't have powders to handle. We don't have molten phases to deal with. We don't really have to worry about thermal events, cooling rates, those sorts of things. And because it's solid state, that allows us to run fairly low power. On our lower power systems now, we're getting welds in the 400 watt range, instantaneous power. So in space, obviously energy is at a premium. The other kind of advantage of UAM for printing in space is it's self-contained. All of the reacting forces can be contained in the motion system that allows for a very tight integrated system, again, without needing being able to handle powders or fuels or any of those feedstocks that may be problematic in space. One area that we've done recently, we're doing some experiments for NASA looking at repair of damage. So let's say the space station, a satellite, has debris damage. We were looking at, can we use this solid state process to repair holes? And we repaired a number of kind of pseudo holes all the way from 1/8 of an inch up to a 1/4 inch. We've actually gone larger now. And all of those repairs with just a single layer of foil were hermetic. Certainly, we weld more foils for structure, but just to get a hermetic seal, we only really need to weld 5/1000ths of an inch of foil over these damaged areas. So that's an area of future research. In the next month or two, we're actually going to be doing some experiments in a full vacuum. So that plastic container at the bottom there is a vacuum chamber we recently obtained, where we'll be doing some tests with the ultrasonic devices in vacuum just to make sure that the physics aren't different than what we assume them to be. But it's an area that we're really excited about, that we're working with NASA, obviously, as well as some aerospace companies on how can we use ultrasound to do both construction and additive manufacturing in space. All right. Last topic, and then I'll open up for questions. We're also doing a lot of work with other additive techniques. I mentioned mixing, powder bed plus UAM or ArcDED plus UAM to build complex parts. We're also embedding sensors for our friends. We have some friends that do a lot of work in powder bed fusion, and they're always complaining about bonds delaminating, builds delaminating, hitting recoder blades because something starts to deform. And we said, hey, would it help you if we could embed strain and temperature sensors inside of your build plate so you could get data throughout the entire powder bed fusion process? And they said, yeah, that'd be a great idea. And here's a video from some work about 2 years ago. This is a custom powder bed system at Edison Welding Institute. But at the bottom, you can see some black wires. Those are actually our embedded sensors coming out of the build plate. So throughout this print job, we were able to get data live on the fly of both strain and temperature as this build evolved. And that allows us to do a lot of kind of quality monitoring as well as looking for defects. So on the right-hand side, you're seeing is actual magnitude of strain along the length of a fiber optic cable. On the left-hand side, you're seeing magnitude of strain via color. And the white line that you see is the path that our fiber optic cable took. And you can see that's kind of like a strain rosette. So what we're trying to achieve is the ability to get both strain magnitude and direction, so the vector of the strain loading in this base plate while the powder bed build was evolving. We put in a whole bunch of other sensors into build plates, but this is a strain-based build plate. I mean, you can see the strain evolve over time. And what we found is, magnitude is interesting, but the vector really pulls out if you have a defect forming in a powder bed build. If your strain vector at one point quickly changes, by 70 or 80 degrees, something's happened from a strain state. So doing a lot of work on quality analysis and in-process build monitoring. But just wanted to give a shout out since there's a lot of powder bed people out there. So with that, I think I will kind of open it up for questions. Again, ultrasonic additive, at Fabrasonic, we do, research development, short run productions, serialized parts, as well as sell these machines.
Well, thanks, Mark, for your great insight on this unique process, as well as AM process combinations. We have some general questions as well as questions a bit more application specific. And interestingly, one question had to do with whether you make assemblies for commercial 3D printers. You just touched on something along those lines with the build plate. And so there are applications beyond what some people might think is, space applications or satellites or things like that. Can you talk about some of the other areas and applications that might not, people might not think of for this technology?
Yeah, actually, our number one application right now is in electrification. We can combine aluminum, copper, and nickel steels, stainless steels, all in a foil type arrangement. And you start looking at a lot of the electrification devices, especially some of the high current devices, being able to get multiple metals very quickly into a foil-based laminate has a lot of advantages for manufacturing of these electrification devices, as well as thermally. A lot of work taking high power electrical systems and building thermal devices around them. So starting with a pre-existing part and building up thermal materials like copper and aluminum, as well as fin structures around a pre-existing power electronic. A lot of work in that area. As you mentioned, 3D printing, we do a lot with sensing for other 3D printing modalities. We love that. Let's all raise everybody's boats together. Lots of fun things. I can't talk about most of those, but it's typically embedding sensors or making a really complex kind of feed through, using dissimilar metals.
Mm-hmm. There's another pretty specific question for you. Can you do radial layering on rounds in the CNC lathe?
Great question. So yeah, we do that all the time. Two of our machines have a headstock, tailstock in them. So your traditional CNC fourth axis. And we've welded on the OD of both pipes and cylinders, as well as, round things that, aren't perfectly round. So certainly you can use a fourth axis to print radially. Typically, we're going to start with some sort of pre-existing feedstock. We're not going to start from scratch on that. So we'll start with a pipe or some pre-existing part, but certainly doable. Great question.
Okay. Here's a more general question. With the capability to join dissimilar metals, are there corrosion concerns?
So anytime you put dissimilar metals together, you're creating a battery if you connect them somehow through air or water or some liquid. So in some of our space applications, not really a concern. Once you launch it, we're not going to have problems. But anything terrestrial, especially anything in water, it is a concern. Typically, what we're going to do is just like in the automotive industry, you zinc plate your steel. We can print a sacrificial anode somewhere in the part and take care of that. So it's really a design question. Certainly the manufacturing is pretty straightforward. We just need to interact with the design folks to understand the use environment the parts are going to go through. And then we can help those customers work through what the best solution, whether that be a sacrificial lamb or maybe a design change so that we separate those metals via some geometry.
Mm-hmm. And can you talk a little bit about the inspection techniques applicable to UAM?
Yeah, so in inspection qualification, that's always the exciting part when you start talking about any 3D printing process. I think what we learn in general in metal 3D printing is that every vendor or every OEM kind of has their own rules and regulations. We're starting to see NASA has out of spec, FAA's kind of got a spec. But what we're seeing from our customer base is everyone's got kind of different rules and different inspection criteria. So it's a little bit led by the customer. But as far as applicable techniques, the most straightforward is actually collecting data during the print shop. It turns out that an electrical device can give you a lot of information on mechanically what's happening in an ultrasonic head. So we can collect data from our mechanical system electrically and put an SPC chart around that. And anytime we see a fluctuation that kind of gets outside of the statistical norm, we can stop, mill off that layer, and then reprint that layer. That's not to say every time you get outside the SPC chart is bad, but for a lot of our high consequence applications, we're just going to stop, mill that layer off. It costs us 5 minutes, and then continue to print right from there. Once the part's done, we can use traditional inspection techniques. Ultrasonic C-scans are widely used by customers. If you want to step it up a notch, a full CT scan, can be done. X-ray CT is done on our parts. And then, some of our customers are going, a step further in doing the, build 10, destroy 5, fly 5. So it's really customer dependent, but your traditional inspection techniques are still valid. It's just some of the times the geometries make traditional inspection a little more difficult.
Okay. Now in your presentation, you talked quite a bit about the ability to embed sensors in printed parts. Can you talk about some of the what people aren't thinking about, some of the areas where embedding sensors would make sense in printed parts?
Yeah, the number one request that we get is actually for calibrating models. I know that sounds silly, but we do parts all the time to calibrate somebody's model, whether that be strain, temperature, vibration, it doesn't matter. I think some of the more unique applications that we're seeing are embedding active elements. So we talked about embedding a servo motor. We've actually embedded active RF elements because we can mill the internal geometries. We can essentially print a waveguide and then embed the active elements and bury those inside of that part, which has some packaging and thermal benefits above and beyond traditional manufacturing. Another thing, we do a lot of tracking devices. Big Brother, National League Baseball, Fox, I don't know who's monitoring them, but we do a lot of tracking devices and a lot of kind of anti-counterfeiting, embedding specific, I gotta be careful what I say, but embedding specific items in specific locations for part identification and avoiding counterfeits. So there's a lot of different ideas out there. Really think about, hey, if I could have an electronic sensor anywhere in my metal part, what would that give me? Can I track its health, how it's doing? Can I track where it's at? Can I get information that improves my process? All of those are on the table.
Well, thank you very much, Mark. I appreciate all your insight in your presentation and again in your detailed answers to the questions. Again, thank you, Mark, and his work with Fabrisonic. And we're on to our next presenter, Amy Elliott, who, as she says, caught the STEM bug from FIRST Robotics, leading to her majoring in mechanical engineering at Tennessee Tech University, where she continued learning hands-on fabrication by building and racing student competition vehicles and interning at various NASA centers. Because of her fabrication experience, she was discovered as channel Big Theory. Amy now has completed the manufacturing demonstration facility of Oak Ridge National Laboratory, where she meets with industry from across the nation to consult them on proper application of 3D printing technologies. She conducts research in the areas of inkjet-based metal and ceramic 3D printing and holds several patents. Please welcome Amy Elliott.
Amy, I think you're muted.
Thank you. Sorry about that. So I just turned my camera on and the internet went out, so I will leave my camera off. Apologies for that. I'm here traveling in a hotel, so I guess the internet's not that strong. So yeah, during grad school, I got this opportunity to be on a reality show called The Big Brain Theory, and originally it was called Top Engineer. I would have never applied to a show called Big Brain Theory. Anyway, it was an engineering reality competition show. There were 8 episodes, 8 challenges, 10 contestants, and it's kind of like Survivor where people get eliminated. And anyways, once in a lifetime experience, and I say that because I'm only ever doing that once. It was so stressful. I ended up getting second place, and Buzz Aldrin was the guest judge for that competition. And, you know, he's second man on the moon. When he saw that I got second place, he took me by the shoulders and he said, "I know what it's like to live in the shadow of another." And I thought that was totally awesome. I mean, Buzz Aldrin just totally equated me to himself. So I thought, you know, hey, I'll take second place for that any day. Because of that, I got recruited for a Science Channel show called Outrageous Acts of Science. It's a fun clip show where we talk about viral videos and the science and physics behind, you know, like how did that guy fall on his face, or, you know, how did she build that cool thing? It's a really fun show. So still doing reruns to this day. And then I was also selected as a American Association for the Advancement of Science, AAAS, an ambassador. So I don't know if you saw all the press around the 3D printed statues of women at the Smithsonian this past March for Women's History Month, but mine was one of those. And actually I got 3D scanned and printed while I was pregnant. So it was really cool to go visit my statue and have my one of my kids with me to take a picture with that statue. Me and my husband are race fans, and probably the coolest thing I've done in engineering is travel to the Salt Flats of Utah and the Salt Flats of Australia to pit for Eva Hakinson. She's a eco-activist in disguise. She likes to build these electric motorcycles and race them and make land speed records. And currently she's the fastest woman on a motorcycle in the world. So it's really fun to go out to Bonneville with her and pit crew. Bonneville's way different from Australia. Bonneville, you know, you're working on the salt all day, it's hot, but you get to go back to your casino hotel and the air conditioning and your casino buffet. In Australia, you've driven 6 hours into the bush, into the middle of nowhere. You're camping at a ranger station. So it's a very, very different experience. But like I said, probably the coolest things I've done. But my day job is at Oak Ridge National Lab. So I really am always learning more and more about how amazing Oak Ridge National Lab is, but it's really a great place to research manufacturing because, I mean, it got its genesis from manufacturing. So we started out with the Manhattan Project, actually refining nuclear materials for the atomic bomb, and that was a rapid transition from fundamental science to actual manufacturing. And so using that heritage and a lot of our big science tools, like we have the world's most powerful neutron beam, we have the world's fastest supercomputer. We have probably one of the best selections of material scientists in the world, best collection of them. And so we're really poised to tackle a lot of the challenges of manufacturing. Some of the challenges that we see just in general is we see, obviously the offshoring of manufacturing, and then all those OEMs are transitioning to late stage production. Product development, and so all of that early R&D is pushed to the suppliers. So we have this kind of decentralization of manufacturing. So we're hoping to provide that place-based innovation. Specifically at Oak Ridge, we have the manufacturing demonstration facility, and that's where we house a lot of our additive manufacturing. Although we have carbon fiber manufacturing and lots of other battery manufacturing, lots of other manufacturing capabilities. But at the MDF was where we do our additive manufacturing. We got our start with plastic BAM. BAM is big area additive manufacturing. And you may have seen this demo. This is the Local Motors Strati being printed. It's a life-size car, and this is being printed live at the IMTS trade show several years ago. Since then, we've printed lots of other things. The Shelby Cobra there is printed along with the house behind it. This pavilion on the center bottom, and then the wet sub there on the bottom right. But the killer app for this technology, as we all know, the top 3 applications for additive are tooling. So probably the demonstration that's really gotten the most traction is this on the bottom left with the wind turbine blade mold. So wind turbine blade molds are massive. They can be like 60 yards long, and they take a really long time just to make the mold because they're made of glued together layers of wood that are glued together and machined down, and they have to wire all this, put all this copper wiring on there for the resistive heating. And when we print them, though, we use way less material. It takes way less time because we're just printing that shell, as you can see. And then also we can add in, as was demonstrated on the previous presentation, we can add in any kind of heat transfer you want into the part. So there's actually slots right on the contour of that mold where you can shove in these reusable heaters and use that to heat the mold. So we saw some really great successes with the plastic BAM. And since then, we have grown tremendously. So we don't just have one big giant plastic printer. We have 5 right now. We have lots of different configurations. We can do thermoplastics as well as thermosets. We do foams. We do all kinds of experimentation on new materials for that system. We also have quite an accumulation of metal powder bed systems. So that includes laser and electron beam, and then also the binder jet systems. And then more recently, we've developed many partnerships in the area of directed energy deposition. That's the welding robots, as you can see there. And then also getting into hybrid machining. So this is our facility. This is the high bay here on the top there. It's kind of like an ever-changing maze. We're constantly pulling equipment out, putting new equipment in, and it's definitely giving our facilities folks a run for their money. But anyway, it's a very exciting place to work. So my area is binder jetting. Binder jetting is a metal powder bed process, and it starts obviously with a CAD model, and then the part is printed using inkjet. So we're not using a laser to melt that layer. We're actually just gluing that powder together with an inkjet print head and a binder. We cure that up, and then we depowder it, literally like an archaeologist, because the parts are kind of fragile. They have the strength of a piece of chalk. So we have to be careful when we depowder them. And then when we've got them depowdered, we need to process them in a furnace just like a piece of pottery. So we can sinter them to full density with some shrinkage, or we can back infiltrate with the second metal. Typically we'll print stainless steel and infiltrate with bronze. And that's how we get our final parts. And there's a lot of advantages to binder jetting. The main advantage really is cost. The process is so fast and the machines are so much cheaper than like a laser EV machine that the cost just comes out way better. So let me move this video, but this was at Rapid a few years ago. The process is very highly scalable. So this is, like a full size engine block there, and then a metal injection molding size or MIM size engine block. You can do large batches, and anyway, there's just a lot of advantage to binder jet, and a lot of work being done on the sintering side. So as we scale up, we need to evolve our sintering technology to accommodate for the distortion that we see. And so there are several strategies for that. One is these sinter setters that you can print in a binder jet machine. You can print this alumina, you put it into your critical features of your part, and then as you sinter it down, those features are maintained by the setter. And then Desktop Metal obviously has the approach where they will print support made out of the same material that you're printing out of, and then they'll put an anti-sintering agent or like a ceramic between the two parts to keep it from bonding, and then you can, the idea is you can just pluck those parts right off. So lots of opportunity here in binder jet. One of the demonstrations we did again was in tooling. We just find that there's just a lot of low-hanging fruit in the tooling industry. Tooling is custom, it's low volume, it's high value, it's long lead time, it's complex. There's a lot of different things about tools that make a lot of sense for additive manufacturing. One of them is the lead time. So, typically when you're making a tool, you have to procure a billet of material that, is bigger than the envelope of your part so that you can, machine it down. And that procurement time can take a while, especially if it's a big tool. Well, with additive manufacturing, obviously we have the right billet every time. It's just a bucket of powder or a spool of wire. And so we can make whatever size part that we need with that. We don't have to wait on that procurement time. And so this demonstration is with H13 tool steel, and it's just an injection molding tool, as you can see. But what was cool is that we put the conformal cooling channels into the print, and it didn't really, cost us much extra to do that. It's a little extra depowdering time. And they were able to sinter that, get it machined down, and demonstrate it on an actual injection molding setup. So that was really exciting. But what was most exciting about this demonstration was we realized just how cheap binder jetting can be compared to laser. So laser makes a lot of sense for aerospace and these really, medical, these really high-end applications. We're talking about tooling or, mass production where you have very, very small profit margins, small liabilities too. And then you need something more price effective. So we got this tool quoted for laser. Just the print itself was $15,000. For binder jetting though, the whole part being made and machined was less than $1,000. So It's just, over an order of magnitude cheaper than laser. And I think a lot of people are catching on to that and looking more closely into binder jet. And then just real quickly, some other things that we explore with binder jet are some of those non-weldable materials. So lots of carbides. So this is boron carbide. And like I said, we have the world's most powerful neutron beam. And one of the things that they struggle with is trying to more or less focus the beam or basically filter out stray particles. And then they do that with these collimators. But boron carbide is one of the best collimating materials, but it's very brittle, it's hard to machine. So typically when they make parts, they're making really blocky, not fancy shapes like here in the center. And then, but when we 3D print them, we can 3D print the powder really well, and they don't really need like a structure to it. They just need it to just kind of sit there. So we can do these very elaborate parts, and in green form is acceptable to them. But we've also experimented with infiltrating that boron carbide with aluminum to make this metal matrix composite, as you can see here. We've also worked a lot on magnetics, so printing magnetic material and then plating that, and then studying the magnetic effects. So rare earth magnets and magnets in general, when they have to be machined, there's a lot of waste associated with that. It's not always recyclable. So being able to print magnets potentially could save a lot of those materials. And then this is one of the cooler videos where we've shown that you can print something like silicon carbide and we've inserted these surrogate fuel pellets into the silicon carbide, and then use spark plasma sintering to consolidate the silicon carbide around the pellets, and shown that you can make these really, really uniform distribution of fuel pellets using binder jetting. And then one more demonstration on binder jet is this engine block. This is for a single piston diesel generator. I believe it's a Honda, and they had been doing some experiments. This is Argonne National Lab. They've been doing some experiments with different types of fuel injection and fuel spark plugs and that kind of thing, and they just needed a new block to do their experiments with. So we were able to cut the block in half, cut it, print it, depowder it, and then fuse it to one piece. And they're currently using that on their setup right now. So one of the bigger topics I wanted to talk about, though, was this idea of manufacturing 4.0. So we know the first, I guess, era of manufacturing was just mechanization and steam power. Then we had the production and assembly line. Then we had automation, and now we have what are these called cyber physical systems. So as we get more and more digital, we have more information about the products that we're building. And so the idea is that you get a customer order, and then you do your design and manufacturing simulation and optimization, not only for the product performance, but for the manufacturing itself. As you're manufacturing, you do your quality and certification. You can create this digital twin because you have so much information about the part. You can call in Uber, or your machine can call in Uber to come pick up the part and send it to your customer. And then, potentially you can do this performance tracking and user feedback through the device itself. So putting all those things into action with additive, you can use that to innovate and improve your product and offer these new data-driven products and services, which is what we call democratization. And the idea is that we are improving faster than the competition can copy. So our efforts towards this manufacturing 4.0 is very, very focused on new systems. So I'll talk about a lot of the new metal systems that we have. So not only just new capabilities, but also investigating these hybrid approaches. So on that front, this is our metal BAM technology. So BAM, again, is big area additive manufacturing. So these are any of the big printers. This is our first one. This is a partnership with Wolf Robotics. And this is a wire-fed MIG welder. And it was, we kind of make it look easy here, but the real trick to make this work, I don't know if you notice other people, or anyone who's doing this, they may have to stop at like a foot of print if they're not, doing this feedback strategy. And that's really what makes this work is as you're welding, the welding process just really isn't very consistent, right? Like it's not really made to be a super smooth thing. And so as you're printing, you're getting a lot of deviations in that layer, and eventually that builds up to the point where you just really can't keep printing anymore. So what they do with this is, and what was really the enabling technology, is to scan each layer and get that profile based on the scan, and then compensate the deposition based on that profile to even out the layer. And so this was that demonstration. We were able to print this excavator boom and put it on an actual excavator and dug around with it to demonstrate it, and it worked fine. We actually did plumb the hydraulics into the print. You can see here on the sides of that boom there. Didn't end up using it, but that was an interesting concept that we thought would be a cool demo, where because on these big excavators, on these big hydraulic machines, those hoses are actually one of the main failure mechanisms. They get ripped, they leak, they get caught on things, all sorts of things. So we thought that'd be an interesting demo. Just to the same point as the heat exchange, as we saw earlier, is very easy to embed these cooling channels or fluid channels into the parts. And then one of the big applications for this are very large castings. So like propellers are a really great example. Propellers for naval watercraft and just big watercraft in general. Those castings can take 2 years, like literally 2 years to make the pattern, make the mold, pour, cast, let it cool, machine it down. We think we can accelerate that to 6 months using this metal BAM technology. And so these are all the different ones that we have today. So we have that Wolf robotic system. We also have American Made's hybrid system. This is a laser and powder end wire. So it can use powder end wire. And the GKN system, this is for aerospace. We'll talk about that a little bit more. But it's also wire, and it has a lot of in situ monitoring that they do for that. And then this one on the right, this is what we call Medusa. We'll talk a little bit more about that, but that's a wire feed as well. More tooling demonstration. So this is just a basic stamping tool for a car chassis. And the demonstration is, you don't have to go, again, get this billet of material and machine it down and waste all that time on procurement and machining, right? Because you're having to machine down a lot of the billet. You can just print this net shape and then machine down, the money making surface, and then use that as a tool. So they've demonstrated that you can print and machine this particular tool in 24 hours. It's worth about $3,000, and it was successfully used on a stamping operation. Since then, we've scaled up. This is a B-pillar tool, and so this is actually one of the most complicated tools on a car to make a car. So this always has cooling channels that go up and down this tool because of how complex this shape is. That they just have to have these cooling channels. And traditionally, to build this tool, you have to cut it in. You have to segment it into many segments that are all machined individually, so that you can drill those cooling channels through the length of those pieces. And so you can imagine it's a very, very complicated tool. Well, when we print it, we can print the net shape. We can incorporate those cooling channels into the profile. This little slug of material in the middle is a demonstration of how we wanted to just print the skin basically, and then backfill with a casting to give it some strength in the middle. But overall, we were able to reduce the amount of time it took. This only took 3 days of printing and then a few days of machining. And we improved the part cooling by 20%. That's something that always kind of comes as a surprise, but then not as a surprise. Is that not only can we improve the manufacturing of this thing, make it cheaper, we can also improve the performance. So that's always an added bonus when you're going with additive, especially for these heat exchange type situations. So apologies, I'll turn that sound off. But this is a demonstration that we did at IMTS a few years ago. It was called a die a day, where we were able to print and machine down a die each day of the conference. And then here's one of those dies being demonstrated at a Whirlpool factory. And as of the last time we checked, it was still working. And so it's a great demonstration of how tooling and dyeing can really come back to the US and be something that's more on demand rather than one of the longer parts of the manufacturing startup process. This is one of my favorite demonstrations so there was a rocket that needed to be launched, but they did not have a nose cone, and they were quoted, a 6-month lead time to get a nose cone for the rocket. These are supply chain issues that have been happening in the recent years. And so what we were able to do is actually print this nose cone in 3 days. And then it took 3 weeks to machine, and that's only because it was a custom setup. We had never done that setup before. So we had to go to the drawing board and figure out, how do we make this work with the tools that we have. I suspect that if it was a routine operation, we probably could have gotten that done in much less time. But nevertheless, about 3 weeks to make this whole thing, and they were able to launch on time, and it performed just well, just right. So the other added bonus of this is that we were able to reduce their buy to fly ratio. So buy to fly is how much material you buy versus how much material you actually end up flying. And so for typical aerospace, it can be anywhere from, like here, it's 55 to 1. So you're buying 55 pounds of material to build that nose cone, but you're machining down 54 of those pounds. And so that's a really high buy to fly ratio. So we're able to reduce that from 3 to 1. So we do that by printing that net shape and then machining it down just to the surface finish that we need. So as promised, here's the Medusa system. I personally think this is one of the coolest things ever. Let's see, my video is paused. So, okay, so this is Medusa. Got some fancy acronym, but we obviously named it Medusa because it's a multi-head thing. But basically the idea here is that when we start scaling up the things that we build, like let's say we wanted to make a big propeller for a ship, we have to be able to build that within a certain amount of time due to the thermal kinetics of what's going on. So as you're welding, the part is going through a lot of thermal stresses and changes. One thing that we learned on the plastic BAM was that you do have to get the part done in a certain amount of time for the size that you're printing. So as an example, the first Strati that we ever printed full size peeled itself apart like a deck of cards. And that's because it took, we were printing it over a couple of weeks. And what we found is when we were printing, pieces of the car, like a quarter of the car, it was printing fine. So that told us that, to print the whole car, we had to increase our throughput by 4 times. We did that by changing the nozzle, the screw extruder, and all the things about the nozzle. And so it's a similar thing here. We're trying to figure out how we can get to higher deposition rates. And one of them is just using more welders welding at the same time. Obviously, you could replace one of these welders with a machining tool and turn this into a hybrid system. But the real focus of this system is trying to get to to a much higher deposition rate. So currently we're at 45 pounds an hour. We want to get to at least 100 pounds an hour. We're doing that through another strategy called hyperfill, which will be on the next slide. And then obviously the major science challenge here, one of the major science challenges is the actual coordinated motion, the kinetics of the system, and how to get everything working together. And then also we'll be doing in situ monitoring. So this is the hyperfill project. Basically, we're just trying to shove as many wires out of the welding nozzle as we possibly can stand. The more you do that, the sloppier the weld gets, of course. So we'll need that feedback, closed loop feedback to actually be able to weld consistently. But right now they're at 22 pounds an hour for one nozzle. And we are limited by the current hardware. So we're really pushing welding technology to its limits. Welders are really not meant to put this type of material out that fast, or they're not meant to have this kind of throughput. And so there's a lot, we're burning out these nozzles. The shielding gas, gets is just limited, and so working on kind of reinventing the wheel in terms of welders so that we can get to these high throughputs. So this is the GKN system, and this one is built to weld titanium or to 3D print titanium. It's a hot wire, it's got a laser, and it's pretty cool. The craziest thing about this one in my eyes is that you have to fill this whole chamber up with argon to weld this titanium. So it takes a lot of argon to do that. And then once you've done it, you're kind of stuck with what's in the chamber. So there's really interesting logistics around that. But basically, the idea here is if we can weld titanium into large structures, we can reduce that buy to fly ratio once again. Titanium being a really, really expensive material and used a lot in the aircraft, the aerospace industry. And so just studying how, we're building up these titanium parts and then machining them down into performance from that. Okay, so now getting into hybrid manufacturing. So there's a lot of different definitions of hybrid. The way we use it is, these manufacturing systems that have both additive and subtractive technology on them. So a lot of our hybrid systems are actual machine tools made for subtractive manufacturing that have then added an additive capability to them. So we have a lot of machine tools like the Mazak, the Haas, and the Okuma here. And I'll talk about those closer here. But basically, the challenge becomes with so many different systems, there's just a lot of different kinematics to choose from. And, in terms of, do I turn the part horizontally or vertically? Does the part stay stationary? Do I move the actual machine tool around it? Do I have a robotic arm? How does my additive process work versus my machine tool? Are they on the same head? Are they separate? That kind of thing. And so we have a whole slew of control systems scientists and machine tool scientists who are looking into these different system configurations and really trying to understand, the effectiveness of each. There are pros and cons to each of the deposition processes. With the wire welding, we see that, we get much faster deposition rates and we can build, much faster. But with the powder, we get much higher resolution. So it's really unclear which route is going to be the winning route. And, they all have their pros and cons. So this is a demonstration of the Mazak machine. So the study was to explore what are the benefits of doing, additive and subtractive in a, swapping back and forth, basically. So doing some additive versus doing some subtractive, or doing some additive, then subtractive back and forth versus doing a straight additive process followed by a subtractive process. So this is that demonstration. What we found was that when we did just an additive process followed by subtractive in that kind of sequential manner, that this operation took 20 hours. Well, if we did hybrid, like true hybrid, where we're making some and machining some, we reduced that to 6.5 hours. So you can see the two different parts there. And so anyway, we also see some differences in properties with this versus traditional machining. But anyway, it's a very, very interesting study to show just the exact advantage of doing hybrid machining. Okay. This is a demonstration on the Okuma system. And then this is a powder blown system. And this one has a rotating axis on the bottom. So we can do these really interesting kind of off-axis printing operations. So yeah, this is just a really neat demonstration of just how fast this can be. And then another advantage, obviously, of hybrid manufacturing is, once you've made your part, you don't have to take the part off the machine and register it into another machine for subtractive manufacturing. The part's already there. You already have it registered in and you can start machining right away. That machine setup process can take several hours depending on the part. And it just seems like a complete waste of time if you can eliminate it. And then this video on the bottom here is just to show kind of the thermal imaging that we do during the print, just to understand the dynamics of the thermals, and eventually we'll want to take that data and use it as a digital twin. All right. So we do a lot of work in our metal additive manufacturing space in computation. We do a lot of simulation, in situ monitoring, data analytics. A lot of that is focused on the electron beam and laser powder bed fusion technologies. We got our start doing that just by watching the infrared signatures and the image mapping of electron beam prints. And so this is a video of the layered data that we would get. And so learning from that, we were able to start training an AI or a neural network to start detecting defects in the prints themselves. So if you see, you know, these little isolated defects, you know, potentially that could be porosity. And so we use that data to create a 3D reconstruction of the part, and then we compare that with CT data. So this is on the left, this is the CT data, and then on the right is our 100 micron resolution in situ data. So that's what we actually took as the part was printing, and then we use those two models to register the part and register our model as well, register our AI. And then using this type of data gathering, we can really gather a lot of information about the part itself. This goes to that digital twin. So we see here on the right the part as like you know, a bunch of, you know, these voxels or these individual, you know, 3D pixels are little file boxes that contain a lot of information. So it takes information from, you know, what we planned to make, what we modeled would happen, the monitoring, and then the post characterization. And all of that data can be used to train our AI. It can be used to inform our simulation even further, and really creating this 3D data framework for additive manufacturing. And then using that in conjunction with our process settings, as you can see on the bottom left here, we can really create this digital thread for additive manufacturing, where we've got the process settings, the simulation, and everything tied together to help us make informed decisions about the product that we're currently making. You know, are we to the point where we've had so many defects that we don't want to continue printing, we need to kill the build, or, you know, hey, this is a good part, it's born certified, let's keep these settings and move forward with that. So with our simulations, this has actually been one of the most enabling parts of our digital thread here, because we use simulation and our understanding of the thermal properties of how, you know, how the things are welded in the print to actually learn about grain structure control. So if you're not a metallurgist, the quick explanation is, you know, your grain structure is really what dictates your material properties, and we really care a lot about what our grain structure is. And so being able to control grain structure is a really big deal, especially on the local level. So that's what we've demonstrated that we can do with additive manufacturing, because you can control the thermal profile of the individual grains as you make them using electron beam. You know, we can actually thread these grains through the parts. So these are these grains here at the bottom middle here spinning. Those are called columnar grains, so they look like little columns. So we can actually make those happen when we want to. And so on the top right there, there's DOE actually spelled out in columnar grains, which are those long ones there, and then everything else are the Equiax grains as shown on the bottom right. And so this is actually pretty revolutionary. This is, you know, feels like the next big thing, you know, the future, because, you know, traditionally you're not able to control grains at this local level. But now think about tailoring not only, you know, mechanical properties with topology optimization, but also tailoring those grains and those grain structures using maybe grain structure optimization in the future. There's that DOE once again. In addition to our new systems that we're developing towards manufacturing 4.0 and the computation that we're using, we're doing some work with interfacing with the workforce. This is just a small demonstration that we did on one of our plastic BAM systems. Sorry if you get motion sick, it might not be a good video to watch, but this is someone walking around with a VR headset, and they're actually able to you know, interface with the machine, look at the build, what it should be, look at what it is, you know, compare. And so the idea here is that we're taking some of the speciality off of the technician. So the technician doesn't necessarily have to know exactly, you know, what's going on. They can just use this augmented reality to check up on prints and make decisions potentially. So so just a demonstration of how you can use hand gestures to work the settings. Voice control is also an option, and just communication with the machine in general using this augmented reality. And one of my favorite kind of examples of manufacturing 4.0 and the Internet of Things is an example that comes from Dr. Tom Purpose. He was with us for a couple years, since gone back to Georgia Tech. But his example is he has this machine shop that his students use, and they have a bandsaw that is set up for soft metals and wood only. And so they have an issue with people trying to cut things they're not supposed to cut on this machine, and one of their student projects was to fix that. So they're actually able to put a very low cost vibration sensor, or just motion sensor on the bandsaw, and actually were able to train their sensor, or train their data acquisition system to determine what materials are being sawed based on the vibrations and sounds of the system, which is really interesting. And so using that connected with Alexa or Amazon or whatever, the Amazon Dot, they're able to actually have this dialogue here. It says Alexa's telling Professor Purpose that someone is cutting with a steel, with a hardness of 40 to 550 Rockwell C on the ME2 2110 bandsaw. So Alexa's basically tattling, right? And so Dr. Purpose is like, all right, send me a note, send a note to my class, and send me a picture of the student, and ask them to see me in my office. So anyway, basically this is kind of Big Brother for manufacturing, but it could be useful, obviously, in a lot of scenarios where maybe you want to put this type of sensor on your machine and learn about the different sounds that are happening, and so a very low-tech way map problems that are occurring. So tool chatter, or maybe this just weird sound happens when something bad is happening, and then use that very low-tech sensor technology to be able to be a part of your quality control in your process. And then things to come, we're working a lot on artificial intelligence for manufacturing, which basically means the machines need to deal with these small variations, small feedstock variations, environment variations on their own. So they need to be able to adapt and keep the process going. So they need to recognize what's happening and know how to adjust. And then after they adjust, they need to be able to verify that everything's all good again. And then using this AI to track, so we're tracking information in the digital twin, and then also being able to flag abnormal deviations, or basically, hey, I don't know what's going on here. Can a human come and help me? So here's just some things that we see in the powder bed arena that we would like the printer to be able to recognize and also correct for. So if you ever worked on a powder bed, there's a lot of things that can happen. One is incomplete spreading. So for whatever reason, your hopper's having a bad day, your powder's having a bad day, and basically you just didn't get enough powder into the layer. And you can have these little pockets of emptiness at the end of your layers. You can get something stuck on the roller, or something scratching the roller, which causes streaking. You can get parts coming off, breaking, and then you can get debris from that. There's a lot of different things that can happen in the layer with the powder spreading that we would like to train the AI to do. So we're using a software called Peregrine to make it easier for folks to train their AIs using the neural net. So basically the neural net is you're just taking a bunch of images, and a human is actually training the AI, telling it what these images have in them, so that the AI can then pick up future ones. And so the reason why we want to use machine learning, obviously, is that it reduces labor needs. We don't need to watch the print on its own. It also removes the human bias. So sometimes we think we know what's going on or what caused the thing to happen, but unless you have the data right in front of you, it's never really for sure. So it'd be great to have that machine learning there to make those decisions for us and be consistent. Here's an example of how we've implemented AI and course correcting, print correcting, and BinderJet. So this is the image of a layer over, it's being spread. It's many layers, kind of, we're walking through many layers at once. And so you can see the green there is the intended print, and then the purple is the incomplete spreading. And so it can actually see and detect when there's short spreading. And at the bottom here is a video of the setting. So it can actually register that there's incomplete spreading there on the purple line, and then it can actually compensate for it by changing the recoder timing. And then you can see that the short spreading went back down to nominal. So this is very exciting for my technicians, since they have to watch out for things like this, or when short spreading happens, we don't always know that it happens, and sometimes we have defects in the part, we're not sure what caused it. So very exciting. Hope to, we're going to be adding more capability like this in the future. And then also using that monitor, that layer data to reconstruct the print as it happened, to be able to register any defects and understand, what we're actually getting out of the printer versus what we asked for. So that is all I had today. Thank you so much, and I'd be happy to answer any questions. Let me see if my video will work real quick.
Well, thank you so much, Jamie, for bringing us up to date on ORNL's extensive AM efforts and the related Industry 4.0 machine learning AI technologies that you're working on as well. We do have a number of questions, a couple right off the bat related to hybrid. Mazak, Haas, Akuma, DMG Mori. Why are there so many machine tool makers working in AM now?
Yeah, I think it's because there's just a clear advantage to the hybrid approach. Their customers and their users can now, build parts directly instead of having to order, order billets of material and, machine them down. It's just a real advantage to the whole manufacturing process.
Mm-hmm. And now you're in the unique position of working on helping to develop these technologies and also using them. For hybrid, are there any challenges you see out there with the process? I mean, is the machining part ahead of the additive part, or things like material contamination, how that's being dealt with? Are there some challenges that are still being worked on with this technology?
Yeah, I don't work directly in hybrid, but I talk to those folks all the time, and I know there's a lot of challenges. One of the challenges is that as you machine something like an additive part, it just changes on you, right? The shape just changes. Those thermal stresses are relieved in the part, and they're very unique to how that part was built versus a billet that was cast and then you machine it down. That's just different. I also have heard many times that darn it, machine tools really don't like hot parts. So having a part that was just welded and is really super hot and then machining it down is a problem for the machine tools themselves. And so there's something that needs to happen in terms of cooling the part as you start machining.
Mm-hmm. So one more question and a sub question related to hybrid. If you could talk about some of the advantages of hybrid AM. And one of the advantages that all of us see are the decrease in machining time and how that's accomplished via hybrid.
Yeah, so like I said, the machining time, the time it takes to swap from like an additive part to a subtractive machine, that time is completely eliminated, obviously. And then also getting into like deep cavities. So like for the hexagon part that was shown, that's actually a pretty deep pocket to machine. And that would take a special tool, and you'd have to go at certain speeds to get to that depth. But if you're just machining, an inch of that at a time, it becomes much faster, much easier.
Mm-hmm. Okay. And we did touch a bit on metal inkjet printing, and in your introduction, we mentioned some of the patents related to that technology. Can you talk a little bit about some of your patents related to inkjet metal printing, and if you could expand on that just a little bit?
Yeah, we do a lot of our IP around materials development for binder jet. So like that boron carbide aluminum system, we have a few patents around that. Collimators, 3D printed collimators using binder jet is one of our patents. We also have a few binder patents, so we custom tailor the polymer and the solvent and everything in the binder system. We custom tailor it to different materials. So one of the binders that's more exciting is actually a sand binder. So binder jetting is actually very widely used for sand. I'm not sure if most people know that, but you go to most modern foundries these days, they have a giant binder jet printer in them. They're printing casting molds using that. So the binder printer the binder patent that we have around sand is actually not only to make the sand prints stronger, but then it's also made compatible with a filler polymer that you can soak the whole part in, and then it becomes as strong as concrete. So we actually had kind of a big media buzz around that earlier this year. We were able to print sand as strong as concrete. And that's great for tooling. So not just like, you wouldn't use this for sand casting, but you can actually use it for like a carbon fiber layup. You can put that in autoclave. You can, you put a coating over the sand tool, and then you can put your carbon fiber layup over it. You can put an autoclave, works great. And so yeah, a lot of our patents are around the actual materials that go into the printer. Hopefully we'll be designing new printers themselves and getting IP around the actual mechanisms, but right, so far it's mostly been materials.
Oh, okay. And I do have a couple questions related to a large scale metal AM. We did touch on some of the applications there. And if you could talk about some applications of large scale metal AM and also the advantages that this process brings to large scale work.
Yeah, so some of the low-hanging fruit for big metal additive manufacturing is obviously aerospace. It's obviously these space launches, nose cones on rockets, and even the propulsion part of the rocket itself. And then also large tools for like stamping, automotive, other things like that. Yeah, so aerospace, I think aerospace and then also watercraft are the biggest applications for LAM.
Oh, okay. And just real quick, I'd like to interject that we will have, you will be getting links to recordings of these presentations from yesterday and today. So I'll look for those in your email. And Amy, I did want to ask how companies can partner with ORNL. How do they go about working with you on various projects?
Yeah, absolutely. We work with companies all over the place. The way that we work, you can pay us directly, or we can do a joint effort where we propose for funding and we do a joint effort. And then also we can do joint proposals for the funding opportunities that are announced by like DOE and other agencies. So there's a lot of different ways to work with us. Doesn't have to cost you a whole lot. We just ask for a cost share on your side that you're also working on the technologies that we're partnered on. But yeah, if you want any more information, if you're interested to partner, please feel free to reach out to me on my email there.
And Amy does have her contact information on screen there, so be sure and jot that down and get in touch with her regarding that or any other details of her presentation. And you finished up with some Gee-Whiz technology and some work you're doing related to AM. Is there something in that you'd like to expand on, or maybe if you could give us a little glimpse or hint of some of the R&D going on that maybe we can look for in the next couple of years related to metal AM?
So one of my favorite projects that I don't want to talk too much about because I don't want to get too hyped over is automated depowdering of binder jet parts. So I don't know if you've ever handled a binder jet part, but they're very fragile, and taking them out of the powder bed is like arts and crafts, right? Like you have to be very careful. You're having to put these, depowder them and put them on, like soft foam, and you just have to handle them very carefully. And it's very tedious, very labor intensive. And so one of our projects is to actually automate that, see what off-the-shelf robotics technologies can enable that. Like, do they have the sensitivity to pick up these parts without crushing them? Can we do that, without people, that kind of thing? And then if there's a gap there, what technology is needed to enable automated depowdering? And so that's really to go for that vision of BinderJet that I think a lot of people have right now, which is, it's a very high throughput process. Some of the BinderJet systems can, print like 1,000 liters an hour. It's very high throughput, but the back end of the process does not meet the front end in terms of being able to process the parts. So now you have all these powder beds of parts. How do you depowder them in a timely manner? So that's really exciting to me. And then also obviously integrating in the AI with that. How does the robot know that it cracked apart? Being able to qualify the part, look at it and scan it in hand, and then be able to put it in the furnace. We also have some technology around the furnace where we're actually able to image, or we will be able to image the parts as they center so that we can learn more about centering behavior, but then also it folds into that piece about board qualified, where we can actually qualify the part before it's out of the furnace and know that it actually went through, a sufficient centering cycle, and all those things. So, yeah, so that's really exciting on the BinderJet front. But in general, we've got most of our machines hooked up into the Peregrine software that we have, which is the software that we use to detect the defects, and then just basically give us those layer images. And so that's really exciting because we're gathering all of this data on all these different processes. So the lasers, the electron beams, the BinderJet, the other systems, we're gathering all this data around all those different systems and really trying to understand, with certain process parameters, what makes it a good part? What are the big knobs that we have to tweak, among a number of other questions that we can answer with that data. So that's really exciting. It's just really tying the whole MDF into this central computer, basically. Yeah, I think those are the highlights. We're working on a lot of different things, but those are the major ones for me.
Yes, certainly plenty going on. There's a lot out there for us to learn, and if we get it wrong, Alexa will tattle on us. Yes.
Exactly.
Again, thank you so much for taking the time to talk to us about ORNL and what you're working on. And we will have one more session beginning at 3:15. Rob Carter is going to be talking about large format metal AM for Army ground vehicle systems. Again, that starts at 3:15, so you have a few minutes to stretch your legs, whatever you like, but please join us here because we'll start at 3:15 promptly with Rob. And thank you again, Amy.
Awesome, thank you.
See you at 3:15. Hi, Rob.
Good
Okay,
afternoon.
well,
How you doing?
good afternoon. Welcome back. Our third and final speaker today is Rob Carter. Rob's an industry leader in research and strategy development for advanced materials and manufacturing with more than 20 years experience in the defense and medical sectors. Currently, Rob works with industry and government on implementation of advanced manufacturing technologies with the Barnes Global Advisors. Prior to that, he was director for advanced materials and process engineering at Stryker Orthopedics, responsible for leading the development of new materials and AM techniques for next generation orthopedic devices. Rob's talk today is titled Large Format Metal AM for Army Ground Vehicle Systems. Please welcome Rob.
All right. Well, good afternoon, everybody. Can you hear me okay? Make sure you see my screen. And with
Yes.
that, perfect. All right. So let me get off this screen. We'll move into, so today's talk, as we were talking earlier, is large format metal additive manufacturing for Army ground vehicle systems. I will actually have to point out that this is a talk that's put together by Brandon Pender, Nancy Hardwick, and I've added a bit to myself here, but be able to talk to what we've been doing in developing a new system that's being developed and stood up later this year. So a little background, I want to start off from where we were about a year ago, give it a little bit of introduction, defining by what we're meaning by large scale additive manufacturing, and then where we're going in these processes, which processes work, which ones won't, and which ones are of particular interest. And then we'll kick into where we are up to today on being able to develop a subsection machine, what we're calling our hull scale machine, and then finally where we actually put the machines to work and do some printing. So a little background, okay, everybody knows the Army uses combat vehicles. A number of them are actually made with aluminum, many are steel as well, but they've been around, they've been central to protection technologies since World War II. As you can imagine, they use very large metal components, cast, forge, form, you name the process, they use them all. Primary importance that it really came in the past decade or two has been underbody protection. In Iraq and Afghanistan, we saw a lot of issues, same thing, but if you actually trace back, that underbody protection has been a concern since vehicles really started. An example of that is that the majority of all vehicle losses during Vietnam were actually from anti-tank mines. So this underbody threat is real, and we've got to figure out and find new ways to develop vehicles and do the manufacturing to improve the protection of the systems. So one of the things we looked into a number of years ago when I was working with the Army Research Laboratory was the expanding that performance, especially the underbody areas, but we had to really start pushing the manufacturing systems. We were looking into thicker hull bodies and new design concepts, and many of these needed new manufacturing processes to enable them. Under one Mantech program that we worked with, we looked into forging, forming, and then newer, higher energy buried arc welding as an example. Welding technologies to allow us to do larger structures, thicker walls, and still be able to process the material. The only thing that you run into is you still have some design limitations. As with any manufacturing process, the manufacturing process capabilities and then obviously limitations impact the design. In forging, one of the things we saw, we were able to create the world's largest aluminum die forging. We were using a 50,000 ton press that resided with Alcoa at the time to be able to stamp out a small swimming pool sized or full combat vehicle hull. As you can imagine, under those type of things, the die itself is actually one of the limiting process parts. It's very fixed. Once you carve your die, the die is cast. You're not making a lot of changes, at least inexpensively. So as you can imagine, there's a tremendous sunk cost into developing the die set to be able to move forward with a forging process. Forming makes a lot of sense. That's a very promising technology. It's been around forever. Basically take plates and bend them. Pretty straightforward. Problem is when you start looking at some of the thicknesses we were going to, you ran into, well, actually getting a plate of that thickness of the materials we wanted, we were pushing the capacity of any of the rolling mills that exist. So we were able to develop a plate thick enough to meet our needs, and then actually finding a system, a forming system that can actually do the brakes and actually bend the part. And then you run into a simple problem of, well, the thicker the plate, the larger the radius on the bend. So that actually imposes some of the constraints on how sharp can the tub walls get. So that changes some of the things when you want to start matching into suspension and underbody connections. So you end up pushing back into welding technologies. Well, again, traditional welds become a source of a lot of potential damage. B, it's dissimilar. Even if it's a similar material, you end up having heat affected zones that weaken the structure. So those still become your initiation for your failure sites. But we were able to show that we could actually go into a new technology that provided cost, time, speed, all the things we needed to be able to demonstrate that we could actually produce a larger, much more robust structure. So we've seen that we got some new technologies, but then we started thinking, what about additive manufacturing? So as we go forward to more recent times and where we are in this current project, is looking into how do we develop and utilize additive manufacturing to enable new design concepts, new structures that hopefully can save us some weight, increase the speed from design to manufacturability, and then overall increase the performance of our vehicles. So as part of this, working with the Ground Vehicle Systems Center, Astro America was able to be a part of this team, also working with Lyft, to award the project to a combined team of Ingersoll, Meld Manufacturing, and Siemens. Ingersoll is developing the machine tools. Meld has a printing head technology that we are very interested in, and Siemens is helping us with the software and control systems. So as we're trying to develop this new platform to push into vehicle-sized parts and make sure that we were really pulling in commercially available technologies, we were really looking into doing tremendous developmental assignments, working into developing a whole new process around it. So we wanted to try to at least assemble something that was at least somewhat mature. So moving forward, why would we want to do this? As I kind of touched on, weight reduction. I don't know, and many people understand how heavy combat vehicles get. Every one of them, obviously, the more weight they have, the more gas they burn, and we've all seen what gas has become recently. We also need to increase the speed and design cycle. So one of the things I think Dr. Elliott talked about in the last talk was when you see, especially with large castings and forgings, those can take years to get into a cycle. We need to be able to short circuit that and provide a much faster time from design to manufacturability. So additive technologies provide a lot of promise in that space. We're really hoping that we can improve the overall performance. And then the next things that we really want to look into is whether you have a much more capable manufacturing process that can do multiple components or hulls, be able to service multiple platforms and even reach across services. So this is not going to be a really kind of a stovepiped single production platform that really only feeds one component or one platform. So as I was starting to touch on, we were looking for something that is commercial off-the-shelf technology to develop a machine that is 3 foot by 3 foot by 3 foot build volume. And then the real hook here is scalable to larger size. And when we say larger size, we're looking something in the 30 foot by 20 foot by 12 feet. So the other thing we were looking into is parts had to be produced with performance equal to those of traditional metal manufacturing processes. We want to see near net shape or net shape parts. The total solution should not be prohibitively more expensive than current processes. And the hardware software solution should be kind of based off of currently available technologies and have a wide capability of material systems. So let's take a quick scan through kind of the large scale. If we look across all the different families of AM processes, a number of them if you don't touch on metals, so that rules out a couple of the material jetting and binder jetting or vat polymerization explicitly are going to be on your polymer side. So you end up looking into, well, powder bed fusion. We know that that's going to have some scaling issues, and any powder-based process is probably not going to be cost effective. So we look into sheet lamination. So Mark, we were paying attention for those that were here for the Fabersonic talk, DED, and then some material extrusion technologies will work in this space. Well, one of the things that we looked into was additive friction stir deposition. And kind of what is additive friction stir? Well, it's somewhere kind of living halfway between material extrusion and a kind of a DED type process. In that, this process really looks into how do you take a bar of metal, have it being twisted, so it's rotating, and then pretty much smearing along. So much like what Fabersonic did, which used ultrasonic energy to drive into it, this one's using very high shear and plastic deformation, very much focused onto the substrate to actually create a new bound layer of material. So you can see this in this substrate right here, you can see these small layers, but I've got a video on the next slide, but you can see where you're passing along a bead of material that is coming down. So basically in this picture, a bar of metal will be coming down, is spinning around, and as the head traverses across, you'll see a new layer of metal being deposited. It is amenable to going up to large scale. It is a room temperature process, and it also works in open air. So there's a lot of attractive features to it. And then as we can port this into a very large platform, now we might be able to reach and kind of satisfy all the demands that were spelled out. So let me go forward and we'll try a video clip. And I don't know if Ali is on here or not. All right. So this is a video clip from Meld Technologies.
Rob, you're muted during the clip.
Ah, okay. Well, my apologies. As I was talking way over here, talking about some of the nice features of it actually moving fairly quickly. We can go back to the presentation. So let me get back over. Is that showing just my screen or is it showing the full screen?
That is showing your screen.
Okay. All right. So as I was talking, that the additive friction stir is a solid state process. There is no melting. This material stays in the solid state. It goes through severe plastic deformation. So you don't have the issues that you run into with a melt or a liquid-based process where you have solidification, cracking, hot tearing, or porosity issues. Also will allow in some cases joining of dissimilar materials. You can run the melt process with two different materials to lay one on top of the other. There are certain relationships that need to be met for that to work. You also end up with lower residual stress state. This was one of the things that really was attractive with large components. One of the fears is obviously if you're building up residual stress, you will have significant distortion, and as you make larger and larger parts, that's going to become very significant, and making sure that you actually can meet the final deliverable for what you're trying to do for tolerances and actually getting the size correct. Also, a wide variety of processable materials. I'll go into that in a little bit. Another really attractive feature to this was it had a solid feedstock. So it uses a 1/2-inch bar currently. So bar stock is commercially available. It's very easy to find, very low cost in comparison to a powder or wire process in many cases. It'll also have fewer health and safety requirements than a powder stock, and it stores a lot easier. You don't have the issue with trying to get up all the oxygen in the room and things along those lines. So it is a very beneficial feedstock to use and very attractive. Also looking at a high throughput process. So as we've been talking on some of the other talks earlier today, talking about different powder-based processes or the ultrasonic approach, right now we're seeing certain materials exceeding 40 pounds an hour with research focused on driving that number higher. And as I was kind of alluding to, it also now you've got a print head that can go onto a very large format machine. So Ingersoll, which is known for producing very large components, is able to basically adapt their process and use a meld head as a print head on a large format printer. So I will not a salesman here. So one of the things I do want to talk about are some of the disadvantages. So you're not going to be able to get the complexity that you can get in systems that use a smaller, I'll say, bead or print size. So some of these, the width of these materials are somewhere 1 to 2 inches, 1 to 2.5 even. So that means you're not going to get really fine features as you see over here on the right. Thin wall structures would require a lot of post-process machining. So from that standpoint, if you're using for large bulky components, yeah, this is looking pretty good. If you're going for finer features, we may have to look into other processes. Limited production capability. Well, there are not a lot of meld machines out there right now. So there's a limited availability today, but then also the scalability. You know, this is, if you're going to be making something in quantities much more than 100, that might be a little bit challenging. So we're going to be working on how do we do the business case analysis and throughput on these systems. And then finally, the unfortunate part is the limited understanding of the material process property relationship. This really is a fairly new process. It is fairly scalable, so we've been very attracted from that, but it does not have as large a database as one would have hoped for both the tensile and microstructures that are generated. One of the things that's unique about this process is that it does change the grain size of the feedstock, and then the final part usually refines it significantly with a lot of texturing put into the area, much like friction stir welding has been done over the years. But you end up getting some really nice properties in many cases in the as processed, as deposited, as well as heat treated conditions. Now that being said, some of the heat treatment will have to be tailored because one of the problems you run into, most of the heat treatments are developed around either cast or forged parts with their microstructures and processing histories. This process history is going to be significantly different. So you will see motivations for grain growth and things like that being a little bit faster. So we do have to do some work on looking at what is going to be the most optimal heat treatment. And the other thing, as with any qualification, how's it going to service over a long period of time? There's not a lot of fatigue data at this point, so that is something we are developing at this time. Now, several of the other technologies, such as the DED suite of processing, so your gas metal arc, plasma, tungsten, WAM, all these different processes that are out there that are directed energy will also be amenable. We looked at this from, you can see relativity space building tremendous structures. Their disadvantage, you do have that melting issue where you are actually have to be concerned with cracking, voids, porosity, some different material systems. Some are good, some are a little bit harder to work with in this space because especially like aluminum materials have a tendency to crack. So they're not really something you want to try to use in this. The residual stress and distortion concerns are significant in this. Building something as big as a vehicle hull or other bulk component, that is going to take some work. It is not a deal breaker, it's just a concern at this point. The advantages are the smaller feature size. Certain systems can get well under 1/4 inch depending on your deposition rate and what your features are going to. So you can get greater complexity and then also be able to go into something with less post-process machining. So from that standpoint, these are still on the drawing board, but I will say they're not the front runner at this time. All right, so I've been talking theoretical at this point. So one of the things that we're looking into is, all right, well, how do you develop these 2 tools? So at this part of the program, 2 tools were desired. I'll say a subsection tool for looking at process of parameters, toolpath, geometry, so a lab scale, something that can be used to prove out what is going to be done with a larger system on a much smaller, much lower cost, easier system to get into. But both systems are built almost identically with their process conditions. So the thought would be that we would have the best transferability from one system to the next. So here are at least some concepts of the 2 parts, and we'll get into a little more detail. The one we call the smaller one, which is the subsection tool, this one is going in at Detroit. And this is going to have the 3 foot by 3 foot by 3 foot build volume. Actually, it'll probably be a little bit bigger than that, but the installs are beginning in June of this year. I'm not sure if we're still holding on to that as well as we would like. There's been a lot of supply chain issues that have slowed down some of the deliverables of certain key wiring harnesses, things along those lines. But I've got some pictures to show where the machine is now and kind of its status of play. The goal is to have this operational later this year. So this is not something that's going to be months or years off of the distance, but just later on this fall. So let's see here's some pictures from earlier this year. So this is the system in assembly. So you can see now you're seeing the back here. You're seeing where the meld head is going to be mounted on. This is the fixturing for being able to do your build volume, your base plate. So this system is becoming real very quickly. This is actually from a couple months ago, so I'd imagine this is probably much more has progressed from here. Here is looking through the back of the machine, so you can see now where the meld head will come down, be able to access the system. Now, the other thing that's going to be interesting with these is that there is going to be a spindle here for machining. So this is actually a hybrid system. It's designed to do that so that you will actually do deposition and then go back and touch up machine. So with this, we can also make sure that we're producing the parts. And obviously here's our meld head is coming in. So it is now being assembled, and many of the meld fixtures. All right, so for the large one, the hull scale tool, that one's being installed at Rock Island Arsenal in Illinois. The target build volume is 20 feet by 30 feet by 10 feet. The installation begins this fall. Operation targeting next year, again, pending some of the supply chain issues that have been occurring, where hopefully we can get around that. All right, these pictures don't do it any justice. We'll get into a few here in a minute that will, but here is the central pylon that the tool and spindle will be placed on, and some of the mounting provisions that go with it. They're functional, and for anybody that has an opportunity to ever tour an Ingersoll facility, I encourage it. It is an engineering playground. They work on things that are just such huge size. It's just, you'll see here in a second. Anyway, so here are some of the different supports and pylons. The rail system that will go into it are being assembled. So you can see this now is starting to take a little bit more shape. Here are your 2 rails that outline the size of the bed. Here are the 2 support columns that are in. Now you're seeing, here's the crossbeam. And to give you some perspective, I believe he's 6'7". So this is not a small piece of equipment. And as of March earlier this year, you can see at least the crossbeam had been installed. I'm 6'2", that's me in the background right there. So this thing is enormous. So very exciting. It's starting to take shape as it has to, because it's going to be installed later this year. very exciting from that perspective. So as I mentioned earlier, some of the different material systems that are out there, MELD has been shown to process of two of the primary materials of interest are going to be your 6,000 and 7,000 aluminums and your titaniums, but they've already covered numerous families, your 1, 2, 5, 6, and 7,000 series, magnesium, copper, titanium, a number of different steels, nickel-based materials, and even some of the metal matrix composites have been processed with a additive friction stir. Basically, as I said earlier, it depends on if you can get it in half-inch bar stock. So that provides a lot easier supply for this to feed the system. All right, well, I wouldn't do much for additive. I only talked about a machine that's going to be built later on this year. So one of the things we wanted to look into to demonstrate the technology is look at a tank hatch demonstration. So you can see here on a fighting vehicle, you should imagine a fairly robust hatch to protect the occupants. What we'll say is this was a hatch derived from an existing design, so it's unclassified. How they make these traditionally, it is actually machined from a forged block. So you would end up forging out a massive chunk of metal and then machining the part out from there. So this is print to near net shape, machine to finish. So process, none of this was optimized for this example, but we wanted to showcase and demonstrate that the capability of the systems and the approach. So you can see here is a computer version of what the drawing of the part is, and I'll say we'll get into this in a minute here, but this is where the print of the part is, and then where that CAD drawing exists inside the deposit. So as I mentioned, this is a rather big piece of metal, 33 inches by 30 by about 10 inches. So a pretty robust chunk of aluminum. And what would end up happening, and unfortunately I couldn't get my video of this to show, they were able to just build it onto a block of material. So again, this is being smart. Now you don't have to deposit everything if you can print it onto a substrate and then carve up the substrate. So you're using your build plate basically as part of the component. So you can see here is the deposit. You can see all the different layers from the MELD process. And then the multi-pass as you machine it out, and as this suddenly goes from a kind of weird looking chunk of metal to a now very much visible hatch. As a result of this, we were able to get this out to AMUG earlier this year, where it won first place in the technical competition. So here are some finished pictures of the hatch, both front and back. So from that standpoint, we're pretty excited about the technology moving forward and also looking into developing larger components. So with that, one of the things that I guess was a question in the last talk was, can you work with us on this? People gain access to this machine? The answer is yes. We are looking for people with ideas of parts. What would you like to build with this? We are wanting to make sure that this system is well used, especially with defense applications, but there are other opportunities that we would entertain. So if you have a part name, a part size, a material type, some of this different information, this team will be able to reach out to you, discuss it with you, see if it's a suitable candidate for being included. And then we can work about seeing how this partnership can grow. So with that, I'll step off. I'm a little bit early, but I think no one will argue with me if we end up a little early today, since I'm the last speaker of the day. And I'll provide some contact information for everybody, and I will turn it back over here for some questions.
Okay, thank you very much, Rob. We did see that in person at AMUG, and it had my vote, and it was very impressive, and it certainly drew a lot of interest there. Now, a couple questions here. We talk about maybe a build rate on the order of tens of pounds per hour. You know, being that a combat vehicle as large as it is, the build would take quite a long time. Can you talk about any work underway to boost the production rate? And also, I would think just having the material on hand and feeding it, if you were to boost that build rate, that would certainly be a challenge. So if you could talk about the build rate and also the ability to provide material for it.
Sure. So as we were saying, we were using a 1/2-inch bar stock right now as the feed stock. There is research ongoing right now looking into increasing the size of that feed stock. So basically the faster you feed a larger volume of material into it, the faster you're depositing material. So we're looking into those. Other ways would be putting an extra head on there, much like in the last talk at Oak Ridge with the Medusa system. You get multiple heads going at the same time. You're scaling your production each time. So that part of this with developing the system is going to be pushing those bounds and defining where can you get to? What is the business case? Basically, because that is, if it takes too long to print, no one's going to use it. So we've got to be able to show that it is a good fit and a good solution to the demands that the Army has. As for feedstock, yeah, I mean, it's, if you can cut a bar or extrude a bar or do anything like that, depending on your geometry, as we scale from a 1/2 inch to an inch or more, whatever the future holds for us, those are all standard bar stock sizes that come from about any source. So as long as we can get it into bar stock, it can be printed in the system.
And I think the goal is to be able to construct an entire hull in one piece in this method. Could you talk a little bit about that? I think the weld areas, the joining areas would be weak points. So if you could just touch on that a little bit.
Yeah, it's kind of interesting because we throw this out there that, okay, you want to build a jointless hull. Well, we're basically replacing the weld area with, now we're building the whole structure out of the weld area. The one thing that it actually does for you is, well, one, if you actually, through the meld process, friction stir welding has been very attractive for years because the weld process actually creates a weld material that is closer to, if not equal to, the parent material strength. So that's one process. So we're looking to use a process that actually yields a higher strength material. And then two, you don't have the stress concentrations. In many of the cases, one of the things that runs a problem is you start concentrating stresses because of your weld zone, which actually causes you a premature failure just because all the load ends up being funneled into an area. And the other one is now you can open up a new design space. So can we go into areas or designs that also promote a better response than just large plate, which you can imagine a large dome of material. If you have a plate with a large blast going on the other side, trying to keep that in place is very challenging. If you put some shape to it, it actually responds better in many cases. So the new manufacturing process opening up a new design space is attractive.
And you did have a list of materials there, and someone has a question here, 4000 series aluminum. They didn't see it in the material list. Can your friction process also print with 4000 series aluminum?
That is a great question. I would have to defer to Nancy Hardwick at Meld to probably get a little bit more detail. I'm not tracking on any 4000 series, and that's not a traditional series for the DoD to look into. Most of our systems are actually based on 5000 to 7000 series aluminums. So I'll have to defer on that one.
Oh, okay. And now this was a specific challenge that this application was designed to meet. What about using this type of technology for non-defense applications?
So one of the things that we're looking into is applicability of the system. So obviously, if we can find top priority are Army applications, next priority is defense applications. but there is opportunity to demonstrate this system. It's at Rock Island. Rock Island can do production or can do part build for commercial entities. So from that standpoint, we are looking for other applications outside the defense sector. So what other industries would benefit from this? You know, we're thinking large equipment, your Caterpillars and things like that. Aerospace would get interested because of, you know, you can imagine, much as Dr. Elliott said in the last talk, fly-to-fly ratios on forging and castings are tremendous. And then just getting time to get them is significant. If you can build now structures that are much more, I'll say, significant in size, plus being in a hybrid system that can be printed and machined to, you know, net shape, there's got to be a lot of good applications for this. So there is opportunity to gain access to these platforms, and we do encourage people to reach out to us, and if they've got ideas, we would be very interested in discussing those.
Well, thank you so much, Rob. It's a fascinating presentation. And again, it was great to see the demo at AMUG, and lots of interest there. And we look forward to, you know, hearing about developments as this project moves along.
All right, well, thank you. I appreciate you having me.
Okay. And this concludes the 2022 3D metal printing experience. 3D Metal Printing Magazine thanks all our presenters today and yesterday, and also our attendees. And we also thank our sponsor, Solar Atmospheres. Again, please remember that an archive of the program will soon be available on our website. And we'll make the presentations available to you, saved as PDFs, in the next few days. Look for an email from us to let you know how to access them. Thank you again, and you may close your browser.